Good evening, everyone. I know it's a bit later than usual, but today we are going to complete the Sieve series, the Sieve discussion, with essentially live coding the Sieve algorithm and comparing it with LRU and FIFO. So before we get into the code, so I'll be coding it in Go today. I want to give you an overview of the test setup that I'm using. The test setup has already been coded, and we'll be essentially plugging in our Sieve implementation to the setup, and then getting the miscount value, which will tell us how good Sieve is in keeping valuable items in the cache and just evicting the unpopular items. So the comparison setup is something like this, where we have our main program, which spawns 3 Go routines. So one is for Sieve, one is for LRU, and one is for FIFO. What these 3 Go routines do essentially is they read from a common trace dataset, and I'll give you an overview of what a trace dataset is well in a minute. They all read this common trace dataset and they apply their caching algorithm on that trace dataset. And what each of them will do is they will keep a track of the miscount. Essentially, miscount is going to be the count of the scenarios where an item was requested from the cache, but the cache did not have that item. So that is a miss, and every time that happens, the count is going to increment for each of the algorithms individually. And finally, again, people familiar with Go will know that Go is all about channels and Go routines. So through the channels concept, we are going to send the miscounts, the individual miscounts back to the main program where we'll print the results. So finally, as part of this test setup, after this 1 hour completes, we will have an output on our console, on our terminal, where we'll actually be able to see the miscount for each of these algorithms, and we'll be able to see that Sieve is performing much better. So with this out of the way, I want to just give you a quick overview of what a trace is and what the trace we are reading today looks like. So a trace is nothing but a file which, when you open it up the first time, it's just filled with numbers. Each line can have one or more numbers. It's not just that it has to have one. But the concept of this trace file for our caching comparison purposes is simply that each number on each of the lines of the trace file is telling us a certain request. So for example, on line number 0, you can see we are requesting for element 0. So we're accessing that particular key value pair. Then on the next line, we're accessing for 14, then 49, 0 again, 41, and so on. So these are essentially the accesses that we want to simulate on each of the different caching policies, and we want to see how each one performs. What you'll also notice, which is something important to pay attention to, is that in these different traces, you will find different frequencies or occurrences of certain elements. So for example, if you look at 0, right, it's occurring many times over and over again. It's occurring here in the beginning, some places in the middle, and at the end it's continuously occurring, right? But if you look at some other elements like 41, it just occurs once and it doesn't come again. So this is an interesting pattern which people from last session would remember that is something that Sieve is actually taking advantage of, right? That only some items are very popular while other items are just, this is again a very common term in caching literature, is one-hit wonder. So they only come once in your cache and they are rarely accessed again, or they're never accessed again. So like 41 is an example of a one-hit wonder in this case. Finally, on the trace dataset, the trace we'll be using today will have around 1 million entries or requests. So that's quite a few, and that will help us get a very solid idea of how Sieve performs and how it compares against LRU and FIFO. So that's mainly it from the visualization, to give you all an idea of what we are going to be doing today. Just before we move forward, I'll just pause here quickly if anyone has any questions about either what a trace is or on the test setup. Okay, we are good. So I'm also monitoring chat just for everyone here. So if voice is not working, feel free to keep typing in chat. I'll be monitoring that as well. So with that, let's actually jump into the code, and I'll give you a quick code level overview of the test setup just to show you how it all connects together and how we'll be plugging the Sieve implementation into it. So just to start real quick, this is the main program that I was talking about. Essentially here, what you can see is we have the different algorithms where we are initializing them. So we have an instance for FIFO, we have an instance for LRU, and we'll also be having an instance for Sieve. And the main idea here is that we want to compare how each of them perform with a particular trace. So that's in the trace runner function. So I'll be showing you that here real quick. So this is the trace runner. So what we have here is it opens the file, which is that common trace file, which I showed you earlier as well in the visualization. It opens that and it reads it line by line. It's just scanning it line by line and it's feeding it into our cache over here. And the algorithm here for feeding it into the cache and checking for misses is very simple. All we do is we first ask the cache if it has the value. If it doesn't have the value, that's a miss, simply a miss because we asked something from the cache and it did not have that value. So we increment the miss count, and obviously like any caching system, we enter that value into the cache now. So earlier it didn't have the value, so it was a miss. Now that it has the value, we are going to set it in the cache so that it's present. And that's about it. The section here for sieve again is left like this because we'll be connecting it later to trace runner after we finish implementing it. And as I mentioned earlier, LRU and FIFO have been implemented. They're typical implementations for either LRU or FIFO, and they all implement just a certain subset of methods that we need for today's demonstration, which I can show you also real quick. It's basically these methods which are common. You have a get method which, given a key, will give you the value and also a boolean to tell you if the value was found or not. You have a set which essentially will add the key value pair to your cache, and it returns a boolean here just to tell you if the value is a new value in the cache or not. So essentially if it's a new value, it's true, and if it's a old value, it will be false. If it was not present, it would be false. And then we have just the length and capacity and stringer. So these are essentially there for diagnostics. And even after this session, when you access the code, you'll be able to take a look and even try out and see how the caches are underneath, like what data they're storing and so on at different points in time. And with that, let's jump into the sieve section of it. So I just have some stub code here. It's just stub code. The main algorithm we still have to write now, which we will be working through together. The stub code is simply that we have the sieve struct where we have our cache. We have the 3 pointers that we use for our doubly linked list. And finally, we have the length and capacity. So the capacity of a cache is simply the maximum number of elements that it can hold. That's it. And length is basically the current size of your cache. So you can imagine that your cache has a capacity for 10 elements. But at this point in time, it only has, say, 2 elements in the cache. So your length will be 2 and your capacity will be 10. Now, the next section here is the nodes, because again, as I mentioned, there's a doubly linked list. So a doubly linked list means there has to be nodes in it. So let's just take a quick look at that. And so here's the node that we have. So in this node, some of it will be quite similar to people present here, like every node has a key and a value. That's the data the node stores. And you have a visited boolean, which is specific to the sieve implementation, because the visited boolean will tell you whether this node has been or this key value pair has been accessed in the past or not. That's essentially what it's for. And as usual, because it's a doubly linked list, you have a next pointer and you have a previous pointer. And that's about it. Just you have a method which creates the node and gives it to you. Nothing special or fancy there. And initially when we create a node, the visited is set to false. The reason why visited is set to false is nothing on my side. It's just the way the sieve algorithm is created. That initially when you create a new node and you add it to your cache, the visited should be false. That's specified in the algorithm as well, which is specified in the sieve paper. So with that overview, I think we have covered what we have for sieve, essentially the stub code that we have. And so let's start actually working through and filling it in. So before we start, there's just one question in chat that I want to address. Yes, the session will be recorded. I will be posting it on the same YouTube playlist, so you can access it from there. And as usual, the links will also be put on GitHub on the same common repository with the code. Even all the source code that we worked through today will be available on GitHub. So there's nothing to worry. It'll all be available even after this session to play around with and to try different stuff with. So with that, I think we are good to get started. So let's dig into it. So the first thing that we should look into is the new function. This is essentially creating an instance of our sieve cache. That's pretty much it. So let's actually go into this. So the first thing that we need to do here is we have to create an instance of this struct. That's literally what we need to do, and we need to return that back. So the first thing I'd like to do, and I feel this is a good practice, is to have a check for sane input values. So in this case, you can see in my comment that if someone tells you the capacity of your cache is less than 1, like 0 or -1, it doesn't make any sense. It's like a nonsense value. So I just want to reject those values immediately. So I'll just be doing that now. So if the capacity that's given as input is less than 1, then for today's session, I just want to panic. I know that we can return errors as well in Go, but for today's session, I think it's good enough to just close it with a panic. So we can just say that the capacity must be greater than equal to 1. Simple. And after this, now that we know that we have sane inputs from the user, we can actually go ahead and create our instance of the struct. So let's actually do that right now. So we have our sieve, which has a key and a value. The key type is K and the value type is V. And let's actually fill the fields of the node in. So the fields of the node, for people who are confused, is all on the right side. It's all on the right window here. So you can see that we have the key, the value, we have visited, next, and previous. And for the sieve struct, which I'm filling right now, the fields are over here: the cache, the head, the hand, tail, length, and capacity. So it's all visible on screen. So even if things feel confusing, just look around. All the definitions will be there for you. So let's start filling it in then real quick. So we have our cache, which is essentially a map in our case. So this is essentially a map where you go from the key, which is of type K, to a pointer to the node in the doubly linked list. So essentially your map has a key as the key that the user gives you, and the value of the map is a pointer to the doubly linked list. That's all it is. The doubly linked list actually holds your value. That's the key point here in this design. The head is nil because initially it's empty, so that is a given. Hand is also nil, which we'll also be discussing again, the hand concept, which is again unique to Sieve. So we'll be discussing that as well in code. We obviously have the tail. So for the doubly linked list, we keep track of the head and the tail. So I'll be marking that as well. And finally, we have the length and capacity. So length is initially 0 because again, the cache is empty. And the capacity is just going to be the capacity because that's given to us by the user. And as usual, we have checked it to be a sane value. So that also is done. With this, we have created a way to initialize our cache. And now we'll actually work through the simple method first, which is get. So all that get is doing in the sieve algorithm is simply saying that, okay, you're giving me a key. I will check if that key is present in my cache. If it is present in my cache, I will do two things. One is I'll give you the value. That's like obvious for any cache. You give me the key, I'll give you the value. But the second thing is special and unique to Sieve. What it will do is that it will mark that entry in the doubly linked list as visited. So I'll show you that in code also real quick so that you get the intuition for this. So what we do is that if the value is present in the cache, right? So I say sieve.cache. So if the value is present in the cache, what we will do is that we will do two things. As I mentioned, we will first, I'll do the easy one first. We will first return the value to the user because that's what they wanted. And we'll even return true because we were able to find the value in the cache. And the other thing which is necessary, which again, as I mentioned, is specific to Sieve, is that we will mark this particular value, this key value pair, as visited. And where is the visited Boolean available to us? It's available in the node, right? So we need to access v.visited. So that is the field for marking the node, that key value pair as visited. So I'll be marking that as true. That's it. So this is the happy path, right? That you asked for a key, the value was there and it's returned back to you. What if the value is not there? So given this is just the get call, if it is not there, we need to return Boolean as false to say that we could not find what you wanted. And the value that we return is a 0 value. So this is just so that, because in this method, right, the return type is v comma bool. So you have to return something for v, you have to return something for the value. So it's common practice in many Go functions or methods to just return a 0 value. So if it's an integer, it'll be 0. If it's a string, it'll be an empty string, just like that. If it's a pointer, it'll be nil. It's as simple as that. So to create a 0 value, I'll just say v, and then I'll just return the 0 value with false. So let me do that now. and that's it. So that is the complete implementation of the get method for sieve. That if it is present, we return it to the user and we mark visited as true for that key value pair. If it is not, we just return a 0 value and false to tell the user that we could not find the value in the cache. Now there's just one more method to go, which is set. But before that, I just want to quickly pause for a few seconds to know if there's any questions about what we have done till now. Any questions, comments, clarifications, you can go ahead and ask now. About sieve, we covered this in the last session, and the recording is also available, so no worries. You can watch that too. But just to give you a context about sieve for today's session, just to keep you going, is that essentially it's a cache eviction policy. So you can imagine that your cache is a fixed amount of storage, so it has a fixed number of slots, you can say, and each slot stores one entry. So the question obviously comes that when your cache is full, right, all the slots are occupied, the natural question is going to be that which slot to empty to accommodate your new element. So this is a very natural question, and to answer that question, one technique is known as sieve. There are other techniques which sieve is compared against, which we have all even heard of, probably in university or online, such as LRU or FIFO. And sieve is just one more technique which is supposed to be number one, simpler, and second is more effective for web workloads, essentially. Let me know if that answers your question, or if you need some more context for today's session. Oh, perfect. Also, if there are any other questions, feel free to unmute in chat or put it in the chat or the comments in the channel. I'll just wait for a few more seconds before we begin, because after this we are done. After set we are done. We just have to plug it into the test setup that I mentioned, and we can then see the numbers. So I'll just wait a few more seconds and we'll continue. Right. So I think we are good with questions. There's nothing in chat and otherwise. So let's continue. So this is the final method that we need to implement for today, which is the set method. And the set method is overall quite simple. All it's doing for you is that it's taking a new key value pair as input and it is inserting it into the cache for you. But again, the only tricky part here is that if your cache is already full, as I mentioned, if the slots are already full in your cache, you obviously have a very natural question here that which slot do I empty to accommodate my new key value pair, right? This new key value pair, where do I put it? So that is where we'll be implementing the exact sieve algorithm. I even have the photo of the algorithm over here for everyone. So you can so we'll be actually implementing that section side by side, and you'll actually see that what's written in the paper can be implemented almost line by line in our implementation, and then we will even run it right in the test setup. So let's begin with the set method implementation. So the first thing that we want to do is that we want to handle the case where if the key value pair given to us is already present in the cache, specifically the key, if it's already present in the cache, how do we handle that case? So what we will do is that we will focus on that case right now. So if in the cache, the particular key is already present, so that means it's already there. What we would like to do is we would like to mention that it's a cache hit because an item was accessed in the cache and it was already present. So we'll do the usual v.visited is set to true. We'll then update the new value, whatever the user has given to us as input, and we will return true, that the value has been set in the cache. The next step now is that if the value is not in the cache, right, that means we're inserting a new entry in our cache, a brand new entry. So the first thing that we would like to do here is we would like to check if our cache is full or not. So as I mentioned, if all the slots have been taken or not. So to simply check that, we can do a simple condition that if the sieve.length, so again the length of the sieve, that is the number of items in the sieve, is equal to the capacity. So if the length is equal to the capacity, then we know we are full. And now it's time to evict something from our cache. So how do we do that? That's where the eviction algorithm on the right is going to come into play. So let's actually look at that. So what we'll be doing is we'll be following along from line number 4. So keen eyes will see here that line number 4 is basically what I have here, what I've highlighted, that the length is equal to the capacity of our cache. And now we come to line number 5, right, where you can say that we are creating a local variable which we are assigning to the value of the hand. So I'll also be doing the same thing. So I create a local variable called hand, and I'll be assigning it to the value of the sieve hand. So essentially this is just a pointer, and the reason why I use a local variable is to make it simpler when you read the code. Otherwise there'll be a lot of something dot something dot something in the code that makes it harder to read. So we just keep a local variable to make things simple, which is called hand in this case. The first check that we do, you can see on line number 6, is that if the local variable is null, we set it to the tail of the doubly linked list, which is also what I'm going to do. So if the hand is nil, right, because nil is basically what we call null in Go, then what I'm going to do is I'm going to set the hand to the sieve dot tail, just like what they say on line number 7. On line number 8, they say while the node which is pointed to by the local variable, while the visited value of that node is equal to 1, we need to stay in this while loop. So I'll also do that. So in Go, we don't have while loops, it's called for loops, but it behaves just the same. So I'll use that. And in my case, I have visited. So I'll say while hand.visited is equal to true. What I will do in my loop, first line number 9, because the element that I'm pointing to, the visited value is 1, right? I'm going to set it to 0. That's what the sieve algorithm does. That if an item has the visited value set to 1, we will not evict it from the cache, but we will set the visited value to 0. So that's exactly what I will also do now. So I will say hand.visited, and I'm going to set it to false. On the next line, you can see on line number 10, we say local variable is local variable.previous. So we're actually moving from the tail to the head. So we are moving one node back now. So I'll also do the same thing. Hand is equal to hand.previous. And finally, on lines 11 and 12, remember that this is a doubly linked list. So when you reach the head of the doubly linked list and you try doing previous again, you'll reach a null pointer, because again, the head node of a doubly linked list has no previous. So in that case, your local variable becomes null. So you have to wrap around. You have to wrap around back to the tail. So that's the important concept here, that if you reach the end of the linked list, the doubly linked list, you need to wrap around back to the tail. And that's exactly what we'll be doing on lines 11 and 12 as per the algorithm. So if the hand is equal to nil, what we will say is we will say the hand is equal to sieve.tail. So we reset back to the tail. That's it. And that completes our while loop from lines number 8 to 12. And now we can continue on from line number 13. So on line number 13, what we're actually doing is we are using the local variable, and we are assigning it back to the initial sieve.hand that we had. So as I mentioned earlier, right, using a local variable just made programming easier, which is also what the authors have used in their algorithm. So we have just followed that, and now we'll be using the actual sieve.hand. So we'll say sieve.hand is equal to hand.previous. So that's exactly what they do on line number 13, and we are doing the same. And now comes the next part, which is line number 14. Now, line number 14, though in the algorithm is just one line where they say discard the node which is pointed to by the hand, which is O, the local variable, from the doubly linked list, that requires, at least in an implementation, multiple more lines. So you can imagine, right, from university or from reading online, that when you're deleting from a doubly linked list, you should know which node you're deleting. Every node has 2 pointers, right, to the next node and to the previous node. So we'll be actually now implementing deletion from a doubly linked list so that we can execute line number 14 of the algorithm. So let's actually do that now. So what we'll be doing is we are going to be deleting the node pointed to by the hand. So what we'll do is that we'll first check if there's anything after the hand. So if hand dot next is not equal to nil, so that means there's a next node. So all of us know that if there's a next node, we need to make that next node point to our previous, because we are trying to delete our current node. So we say hand.next.previous is equal to hand.previous. The else case here again is quite trivial. If our current node doesn't have a next, that means we are the last node of the linked list, right? Think about it. If hand is our current node and it has no next, What that means is that we are the last element of our list. So in that case, we are the tail and you're deleting the tail node. So if you're deleting the tail, we have to update the siev's tail pointer, which we will be doing now. So sieve.tail is equal to hand.previous. And this is essentially the deletion from the next pointer perspective. There is one more, which is obviously from the previous pointer, that is the previous node. So if the hand.previous is not equal to nil, so what this means is that there is a node before the hand, and if there's a node before the hand, that node should not point to us anymore. It should point to the node after us because we are deleting the node pointed by hand, right? So we'll just do that now. So hand.previous.next is equal to hand.next. So we are deleting it from the previous node. And the else case again is simply that if your current node hand doesn't have a previous, that means you're the first node, because the first node of a doubly linked list doesn't have a previous, and you're deleting that first node now. So you need to update the head pointer of the sieve. So we'll be doing that now. Sieve.head is equal to hand.next. That's it. So this is just deletion from a doubly linked list. All these lines that I'm highlighting here, it's just that, it's nothing more. And after we have deleted it from the doubly linked list, we just have to delete it from our map. Because again, if I just show everyone here to recall, we have two parts in our sieve. We have obviously the doubly linked list, which we have head, tail, and hand. And we have our cache, which is our map. So we need to delete it from the map also. So I'll be doing that right now. So I'll take a new line and I'll just call the delete. So sieve.cache, so that's the map. And I'll say hand.key. Because again, the hand is a pointer to the node, and we know that every node holds the key and the value. You can see it on the right here. Every node has the key and the value. So I'm just accessing that deleted from the cache, deleted from the map. And obviously, because I've deleted an element from my cache, I have to reduce my length by 1. So I'll just do that right now. And that's it. So now I have evicted an element from my cache. So again, it might be a bit amusing to people here that in the algorithm, it's just one line, which is discard O and T. But if you actually look at the implementation, it's multiple lines that have to go into it. So this is essentially what we do. We delete from the doubly linked list, and we also delete from our map. And that's the eviction. That's line number 14 for you. The last part here is essentially line number 15, where we insert the new value into the head of the doubly linked list, which is the incoming key value pair, right? Which comes to the set function call. So we need to add that to our doubly linked list, and we'll be doing that now. So the first thing I'd like to do is I'd like to create a node for this new element. So I'll call it NN for new node, and we'll just call the new node call. I'll pass the key and I'll pass the value. So this will create a new node for us. And what I'll do is I'll insert this into my cache. That is the map essentially. So against the input key that the user has given me, I will put the new node. And then what I will do is I will insert this node into my doubly linked list. And where, as per the sieve algorithm, the node has to be inserted into the head of the doubly linked list. So we'll be doing exactly that now. So I'll say the next node dot next is sieve.head. So I'm essentially making it point to the head node. If the head node exists, if there is something there, sorry, this should be head, then that node's nil, so that node's previous has to be updated. So I'll just do that now. So essentially what I've done here is I've said that, okay, my new node's next should be the pointing to the head of the sieve. And if there is already an element at the head, that node's previous should point to me. So again, it's just a doubly linked list where when you're inserting a node, you have to point to that node as next, and that node has to point to you as a previous. So that's essentially what's happening here. And finally, again, we need to update the head because you're the new head of the doubly linked list now, because you're inserted at the head as per step number 15 in the algorithm. So I'll just do that now. And last, again, this is just a doubly linked list detail, which we need to have to implement the sieve algorithm, is that if you're inserting the first node in your doubly linked list, then even you have to update the tail pointer. So that's exactly what we do now, that if sieve.tail is equal to nil, that means that initially the doubly linked list was empty, your cache was empty, and this is the first element in your cache. So we need to update the tail as well to point to this new node. So sieve.tail is equal to new node. Finally, we just update the len and we return false. So false essentially signifies that the node was not there in the cache earlier. No, this should be val, yeah. So false just signifies that the node was not there in the cache earlier. We have inserted it now. And true signifies that it was there in the cache earlier and we have just updated the value. That's all the Boolean value from set signifies. So this is pretty much the implementation for set. I would say that out of all the three functions we have written, set is definitely the most involving because it has, number one, we implement the algorithm that is there from the paper, as you can see on the right hand side. And there's a bit of doubly linked list manipulation that needs to be done. So that always gets a bit tricky without visualizing it as you write the code. So that is just one thing to keep in mind. But otherwise, everything else is quite straightforward from the implementation, whether it's the get function where we mark the visited value, or even just constructing the initial sieve struct instance. So before I move forward to the final step where we actually plug in our sieve implementation to run against the trace, I just want to pause it again just for a few seconds. If anyone has any questions, feel free to unmute or write in chat. I'll be monitoring chat as well. Also, if everything's making perfect sense now, feel free to react on Discord with a thumbs up. It gives me a good idea of if people are able to follow along, if there's something I need to clarify, because we have time still. I think we are still good on time with half an hour. So if there's anything we need to cover, we can do that too. How is eviction different? Perfect. So on the eviction different from LRU, so mainly again, from the last discussion, the main point about sieve that you need to keep in mind is that in sieve, there is a new pointer that we use called the hand. And the key part of the hand is that it actually scans your cache from tail to head to find an element which has a visited value of 0, and it evicts that element. So the benefit of this approach of using a hand, right, which keeps moving in your cache, is that it can find elements which are newly entered into your cache and are not very popular. So it helps in something called as a quick demotion. So it quickly removes elements from your cache. And it also helps in making sure that your cache only has items which are popular. So popular items are essentially items which are accessed often, and they also live a long time in your cache. So it's a dual effect there. So that is the main point of the hand. And the second part about sieve, which is important, which makes it again very special, is something known as lazy promotion. So lazy promotion is an interesting thing to look at. I can even show you in the code in just a minute. What you'll notice here, right, for sieve, as we wrote the algorithm, was that when we accessed an element in our cache, and it was a cache hit, right, it was present in our cache, what did we do? We just set the visited value to true, and we returned back. If you notice, we didn't do anything to change the cache. We didn't move any elements around. We didn't manipulate our doubly linked list in any way. We just set one Boolean to true. But if you look at LRU, right, this is the implementation of LRU which I did earlier. And you don't need to know the specifics of this. This is just a simple LRU cache implementation. The main point that you need to focus on what I'm sharing is that in the same LRU algorithm, when you do a get function call and you get a cache hit, again, you access the cache and it's present in the cache. Look at how much of work you're doing. You're actually taking the element from your doubly linked list. You're moving it to the head of your doubly linked list. That means you're moving it to the newest area of your doubly linked list, so that it's as far away from the tail. Because in LRU, what you do is you actually always evict from the tail of the doubly linked list. That means elements at the tail are removed from the cache first. So what LRU does is it removes the element that was accessed from the doubly linked list, wherever it is in the doubly linked list, and it inserts it into the head of the doubly linked list. And this happens on every single get call when you get a cache hit. So this is basically something known as eager promotion. And this is a very bad property to have for web workloads, especially web workloads. So this is something which sieve doesn't do. Sieve does something called as lazy promotion, which, as I showed you here, it doesn't do anything with your input. It just marks it as visited and it moves forward. So this is actually a good example of less is more, right? You do less work, you're actually getting more benefit, more improvement in your performance. So that is mainly the difference between sieve and LRU. Let me know if that makes sense, or if there's something else which you have a question on, and we can discuss that. Perfect. So I think with that we are good on time. and work to get the final part of our test setup done, where we'll be actually plugging in our Sieve implementation that we did now on stream to our comparison setup. So it's quite simple to plug it in. It'll be very similar to what we have for LRU and FIFO. So I'll just keep it consistent with that. So first, what I'd like to do is I'd like to create an instance of my LRU cache. So I'll also do that here. So I'll call it Sieve cache to keep things consistent. And I'll say sieve.new Sieve cache. And here it's a string. So what this means is that the key is a string and the value also is a string in my cache. That's all it means. And I'm setting it to a common capacity. So the capacity is the same for everyone, whether it's LRU, FIFO, or Sieve, the capacity is the same. The next part is my channel, which is the Sieve channel. As I mentioned earlier in the test setup, every Go routine has a channel where it can set its miscount back to the main program. So I have that already here, which is called the Sieve channel. I'll just move it one line up. And finally, we need to call the trace runner. So this is not necessary. None of this code is necessary. This is just stub code. So what we'll do is we'll call the trace runner again. We'll pass the common file name, which is called trace. We'll pass in the Sieve channel, and we'll pass in the instance of the Sieve cache. So essentially with that, we will have the implementation. So with that, we should have the implementation done for comparison. So I think the only piece left here is to actually try running a build to see if everything is going fine. Okay, so the build passes, and with this we should be ready to run our trace runner and actually see the miscount values. So we'll be seeing the miscount values for all three: FIFO, LRU, and Sieve, and this will be on the same input trace data set. So let's just see that now. Okay, so here's the values, here are the values. So what I'll do is I'll just create a new file and I'll just paste it here so that I can sort of expand it for everyone on stream. So this is essentially the miscount values for each and every algorithm that we had on the common trace. So you can see that the miscount for Sieve is around 4051. That's it. And remember, our input trace had 1 million entries. So out of 1 million entries, only 4051 entries were a cache miss. While if you look at FIFO, which is, you could say, the most naive of the three algorithms, it has, if I get this right, 673,000 misses, which is a lot more. You could say that's actually more than 50%, because technically we have 1 million elements and 673,000 is more than 50% of all requests were a miss. And finally, LRU. So LRU again is a bit better, marginally better, you could say. And in LRU, what's happening here is you can see it's 621,000, around that much misses. And that's a lot. Again, it's more than 50%. So more than 50% of your requests are all missing in your cache. So you can see that in web workloads, where again, certain items are very popular, while many items are not as popular, which is a very common pattern seen in web workloads, Sieve performs exceptionally well compared to FIFO and LRU. You can see that it's almost night and day of a difference in terms of your caching performance. So this is mainly sort of the takeaway from the live coding session, that how the miscounts change when you use different implementations of the algorithm. And yeah, sure, I can show the trace file as well. It's very similar to what I had in the whiteboard. So let me just open that for you. Okay, yeah, it's a big trace file, so that was sort of expected from VS Code. So let me not worry too much. Let me close this so that it's visible to everyone. So this is the trace. So what you can see here is essentially every line has a certain element access, and this continues for 1 million lines, and we pass each access to the caching algorithm to see its performance, to see is it a cache hit or a cache miss. So some things here that we can actually see immediately right off the bat is 0 is very common, right? You can see zeros appearing multiple times. There are certain elements which don't appear very often. For example, if I search for 43, okay, it does appear multiple times, but it's not very close to each other. So it appears once on line number 11, 43. Then 43 appears on line 239, and then so on. So you can see the elements frequency of occurrence also is different. and in such workloads, it performs better. No, so like line, no one is caching a key 0. So essentially, um, the key 0, yeah, we could say that maybe LRU and FIFO are evicting the key 0 very quickly. So that is a possibility in our case, that because of so many inputs happening, and again the same sort of distribution, right, where some elements are very popular and many elements are unpopular, while some are very popular. It's possible that LRU and FIFO didn't hold the value 0 for very long. So because of that, 0 was removed from the cache, and the next access of 0, which is very common, would have been a cache miss. So it increased the miss count a lot. So yeah, that is 100% a possibility. And I think 0 was not the only sort of element for this. I'm sure there'll be multiple other elements, probably like 43 and so on, where we would see the same sort of behavior, that they are popular, but because of this distribution that web workloads have, they would have been removed from the cache and they would have caused consecutive misses afterwards. Okay, so the capacity of the cache in the test setup, so the capacity was 30 for all three of the caches. And okay, can it be said that Sieve is better than LRU, or does it depend on data type and distribution? So okay, so mainly for web workloads, which is essentially web caches. So if you're looking at CDNs, or if you're looking at any key value cache for a website or a web server, so for example, what Twitter, Facebook, and so on use, Sieve is hands down better than LRU. But if you're looking at workloads where you need a long range of consecutive accesses, so imagine you're opening a large file on your operating system and you're accessing multiple pages of your OS, right? Consecutive pages of your OS. In that case, Sieve performs not as good. And in those cases, LRU actually performs better. And there are certain variants of LRU as well in literature, which also perform much better than Sieve. So if you're looking at web style workloads, again, CDNs, web caches, Sieve is a good option. Like, it's a solid option to try. But if you're looking at more of system related workloads where you have these long range of consecutive scanning of data, like reading multiple consecutive pages from the operating system, then Sieve will suffer in performance and LRU may still be a better choice. And okay, shouldn't the capacity be higher? We can increase the capacity. I had tried it with multiple. I had just used 30 for demonstration, but I don't see any reason why on stream we can't make it larger to say 300, right? Let's make it 10 times more just to begin. Let me also reduce the size of this so that we can see both of them side by side. So yeah, what I'll do is I'll just rebuild the program and let's run the trace runner. Yeah, you can see the performance is still quite good for Sieve, and it's still quite bad for the others. You can imagine that for LRU and FIFO, you can imagine still a quarter of the accesses are still missing. We can even make it 3000 just to take it up a notch again. So let's just build let me clear the screen. Let's build it and let's run it again. Yeah, now it's sort of becoming similar. But again, here you need to kind of take in the fact that in case of Sieve, right, we could keep the capacity quite small, which means we would take less amount of memory, but we were still getting very good performance compared to FIFO and LRU. But to make FIFO and LRU similar to Sieve in performance, we actually had to increase the size of our cache quite a bit. Then only we were able to make them equal. So there's also that important part to consider, that you can't make your cache very large also in your system. So if there are constraints, Sieve is still much better. You can have a much smaller cache size and still have radically better performance than FIFO and LRU. Again, as I'm answering the questions, I know I'm not pausing in between, but feel free to let me know if that answers your question, if there's any follow-ups. There's no issue at all. We still have enough time to discuss. Perfect. The unique number of elements, I hadn't got a count of that earlier, but I can check back and let you know after the stream on the unique number of elements in the cache. Sure. So about 5,000, right? Actually, let's give it a go. Why not? So I've set the capacity to 5000. I'll rebuild the program again and let's run it. Yeah, it's the same again. And right, we can keep increasing it. I mean, probably the limit would be, I think, 1 million. So 1 million would be you cache all the elements that come in. The first accesses will always be a miss, right? So there'll be still some misses that happen. Because the first time we access that element ever in the trace, it will still be a miss. So that would be a problem. So we can take a look. Okay, yeah, it's 1000. Actually, on another hand, we can use this to find the number of unique elements. Yeah, to find the unique elements, because when they're because the first time an element ever is encountered, it'll be a miss because it's the first time we ever encounter the element, and you can see the miss is thousands. That means we encounter a unique element 1000 times, and after that it's just repeating. So yeah, that's 1000 unique elements. That's correct. Yeah, just to remove any confusion, it's 1000 unique elements, and the reasoning is very simple. That our cache size is 1 million and our input trace also is 1 million. So there is no chance of a cache miss happening once an element is in our cache. So once an element is embedded in our cache, it's never going to be removed because we have enough space. So what's going to happen is that the cache miss is only going to happen when we encounter an element the first time, which is the number of unique elements essentially. So in our case, we can see the result is 1000. So we know there are 1000 unique elements. Cache size to less than 30. Yeah, sure. Let's just start with probably 10. So we have 10 and let's run it. Yeah, again. I hope this is still visible to everyone. Let me see if I can zoom in a bit. Yeah, so Sieve again performs much better. FIFO is quite bad. 817,000 accesses are missing, and LRU's not really much better. 789,000 misses, which is a lot. That's like, I think that's more. Yeah, that's more than 3/4 of all accesses are missing. So that's quite bad in terms of performance compared to Sieve. So the question on what we're discussing, essentially we are completing the second session for Sieve. And so Sieve is essentially a paper from Usenix conference, NSDI if I understand correctly, where they talk about a new caching policy which deals with how to efficiently remove elements from the cache, so that the elements that are left in the cache, because when you remove there'll always be something left behind. The elements left behind in the cache are popular elements and will be used in the future very often. So the sole purpose of that is to reduce your cache misses so that your cache is more effective, because more data that you're searching for is in your cache already. And we are today basically implementing it. We implemented it in Go, and we compared it with the FIFO and LRU algorithms, which are very popular from university and otherwise. And we were comparing their performance on a trace data set. About the question on caching software, so Sieve has been implemented for many popular caching tools. I believe there are implementations today for, maybe I have this open with me. Is it from this? Yeah, so this is the website actually of the authors. This is the GitHub page that they maintain, and they've actually implemented it as part of different caching libraries. So these are very popular caching libraries in different languages. So if you're familiar with Rust, Python, Golang, JavaScript, C++, you would have heard about these, and it's actually implemented in these libraries. So if you're using these libraries, you can actually use Sieve in them now. And yeah, it's mainly preferred for web workloads. So web workloads are anything where you need to have a web cache. So say for example, you have hosted a web server where you're allowing users to access some data. But rather than going to the database every single time to get the data, because that's expensive, you can store the data in your cache, in memory in your cache. So when the user requests for that data, it's in the cache and you can give it to them quickly. So in that web workload, you can find Sieve to be very effective. Another case is in case of CDNs, which are like content delivery networks. So they allow you to have your website data, your static data very close to users. And again, their sieve is very popular because there are certain websites which are very popular. People access them every day, every minute, every second, possibly in today's day and age. But there are certain websites which are not very popular. People won't access it every day, maybe once a week, and so on, which don't have to be held in the hot cache. They can be loaded from backend whenever needed. It won't be as expensive. Regarding cache capacity, number of misses. Yeah, so there are actually graphs, I believe, in the paper. You can this I think is the graph I think you're talking about. So I hope this loads. Yeah, so this actually is, I think, what you are referring to, right? That you have essentially the cache size in bytes, and you have the miss ratio, and you can actually see that obviously as your cache grows larger, the miss ratio should go down because you have more space in your cache now, less number of times you need to evict things, but you can still see that consistently Sieve is performing better, and by a good margin. Like, look at the gap between the red line for Sieve, the red dotted line for Sieve, and the other lines for FIFO, LRU, and so on. So I hope this answers your question about the plotting. So this is essentially what we are looking for. And about the question for Sieve, there is a recording for the previous session where we went over Sieve. So if you see over here, so this is the YouTube link actually. So this is a link where we recorded the entire session, the entire discussion. So you can actually see this recording. It's about an hour long. Every session is an hour long, and you'll get the full context of Sieve and the implementation. I've just linked it in chat as well. Right. Okay. For operating system workloads. So for operating system workloads, the reason why it is bad for operating system workloads is essentially because of a property known as scanning workloads. So scanning workloads are essentially workloads where you're accessing a large amount of data, and all of that data is contiguous. So what's happening in this case, when large amount of data is contiguous and you're accessing it, you'll have a lot of cache misses initially. You'll have a lot of cache misses. And because of those cache misses, there'll be a lot of pressure to create space in your cache for those elements. And because of that, what happens, an unfortunate side effect of that is a lot of elements in your cache, especially the old elements, they will get wiped out from your cache. They will get cleared out to make space for the new elements. And Sieve unfortunately has no protection against such a workload. And because of that, your cache kind of gets, in a way you can say, flushed with garbage elements which won't be accessed in the future again. As I was saying in the earlier part of the stream, right, one-hit wonders. And those old elements which were very popular, they'll not be in your cache anymore. And you'll have to again load them in your cache, so you have cache misses again. And that's the reason why they're not good for these OS type workloads. We are loading a lot of pages from your operating system, and all of those pages are contiguous. Think you're opening a large file of multiple megabytes. You're streaming a video, right, of GBs. So in such cases, let me know if that answers your question, or we can even try thinking of an example for understanding it better. So LRU would be better at this simply because LRUs has certain variants where they maintain actually multiple LRU queues. And what they do with these multiple LRU queues, right, is they're able to keep elements which are suddenly flooding the cache separately from elements that are consistently popular. So in a way, it's kind of giving that isolation so that when you have these sort of scanning workloads, your cache doesn't get flushed with all these one-hit wonders, and you don't lose all these very popular elements which have been in your cache for a long time. Those elements will stay in a separate LRU queue. So you can think of it as everything starts in a common LRU queue. Very popular elements get promoted to this sort of VIP LRU queue, which is a separate LRU queue. So when you have these scanning workloads, these elements in the VIP queue won't be affected, right? Because they are in a separate isolated queue. All these incoming one-hit wonder elements will all fill the common queue. And that way you have that protection. And that's how they prevent issues with scanning workloads. And about the queue, the multi-queue method which I was talking about, there are many algorithms that do this. Some with 2 queues, some with more than 2 queues also. But that's the whole idea. How a separate queue? Oh, okay. So the idea is that if an element in your LRU cache is very popular, right? Like it's consistently being accessed multiple times, you can move it to a separate LRU queue. And that separate LRU queue is like a separate entity where you only keep these very popular, very frequently occurring items. And as I mentioned, right, items only go there when they're very popular. So when you have these scanning workloads where multiple new items are coming at once, those will not occupy this separate queue. They will occupy the common queue, the earlier common queue. So these very popular items, frequently occurring items in this special queue won't be affected because they're isolated in a separate queue. And coming to the second part of your question about why it can't be in Sieve, so the thing is, authors have not discussed this idea yet. They do talk about it being possible. I think if I have the paper, I should be able to show this. They do talk about this as future work, if I may be precise here. So they actually talk about this under, yeah, Sieve is not scan resistant. And you can actually see it mentioned over here as a ghost cache. So this is the exact part which you're looking for. So it keeps a separate shadow cache, which is like a separate queue. And it keeps track of these recently evicted items, which are your popular items. And because of that, it's able to make smarter decisions. And this is what you need essentially, because when you have these scanning workloads, you're flooded with multiple new elements coming at once. So you need this shadow cache, this separate queue to keep track of the popular elements so that if they are requested again, you have them present. So this is kind of like a future work in the Sieve paper. You can make modifications to Sieve to have this. Multi-queue LRUs. Yeah, there are actually multi-queue LRUs mentioned in the paper. So I think, let me see. I think it's multiple LRU. Yeah, so these are the ones. So ARC, SLRU, and MQ, they use multiple LRU queues. So if you're interested, you can look at these algorithms, and probably I can paste this in chat as well, just as a mention, so that it's easy to search for these names later. So again, caching is a very popular sort of field for research. A lot of new things being tried out. So this is like another sort of subfield, right, where you look at multiple LRU queues and you see how they perform. It can be 2 queues, it can be more than 2 also. The whole idea is that you have a separate place or places where you keep these popular items, so that if you have these sort of scanning workloads where you have a flood of new items coming in, these popular items have already been moved to these special separate queues so that they don't get evicted essentially. So Sieve doesn't have this, like they didn't implement it in the paper, but they do mention it can be done, and they call it a ghost cache. You can see this here. But in case of LRU, it has been done. There are variants of LRU where people have done it, such as ARC, SLRU, MQ, and so on, where they have used multiple queues and they have made it such that it's resistant to these scanning workloads to a very good extent. And about the second part of your question about LRU and Sieve being used together, so in the paper at least, they don't talk about LRU and Sieve being used together. It's actually like LRU is used separately, either as a single queue or multi-queue, and then Sieve is separate with a single queue only. Multi-queue is left out from this paper. So scanning workloads essentially are workloads where, so they're essentially called block cache workloads, where you have, so you can imagine it like this. Imagine you are opening a video file which is of multiple gigabytes in size. Now, if you think of it from your operating system terms, right, your operating system is loading those gigabytes in terms of pages. We all know from operating system, we have this concept of pages, right? So you're loading pages from your storage, right? Now, what is happening is you're loading these multiple new pages from your storage into your memory, right? And you're caching them there. Now, what is happening is that your memory is limited, your RAM is limited. So in your RAM, you will have some popular items. That means maybe some application which you constantly use, maybe some pages for your operating system, which are obviously important because your operating system is always running. And then you have some remaining free space for the pages of your video application to come in, right? Now, what is happening is that you have these multiple new pages coming in for your video, which you're playing, your multi-gigabyte video. And because of that, these new pages, these new objects, they are mixing with these popular objects that were in your RAM, in your cache for a very long time. And what's happening in this case is your operating system now is under pressure to create space in your memory, in your RAM for these new pages, because otherwise, how is your video going to play, right? That's an important point to think about. So, because of that, your operating system has to now evict all these popular pages. So, what happens is that many pages in your RAM get evicted, including your popular pages. And because they get evicted, when your operating system, or say for example, some very common program that you use needs those pages, it's a page fault. It has to again go from storage and it has to get those pages. So in scanning workloads, you have these large amount of new items coming into your cache and they are completely flooding your cache. So your cache is kind of pressurized to remove everything that it has. Popular, unpopular, it doesn't matter. Everything has to be removed to create space for these new incoming items. And because of that, you lose your popular items, obviously, because you have to remove everything from your cache to create space for the new stuff. And consequently, when these new items are useless because they're not used again, your old items are gone and you continuously have cache misses afterwards. So that's essentially what scanning or block cache workloads are. And as I mentioned earlier, the way to solve it is with a separate queue or a separate cache, which they called a ghost cache, where you store these popular items separately so that they don't get affected, essentially. Let me know if the video example answers your question, or if not, we can take probably another example too. There's no issues. Because I think in general, any big workload you have, it can be a problem. Imagine you're playing a big game and you have to load all the game textures into your RAM. It's a problem. Your browser, also, you have so many tabs, each one is contesting for space. That can be a problem again, where you have these huge amount of scans happening. So these are kind of the workloads where Sieve doesn't perform well. And these other multi-queue approaches perform superb. They perform very well because they're able to keep these popular items separately, right? And the moment you can separate your popular items out, you have this benefit where you can sort of make sure they don't get wiped out when scanning workloads come in, because you have protected them in a separate place. Yes, they're used in multiple places and they're used in different languages. That is correct. This is also, I think, mentioned on their GitHub page too. I think it's, if I just come over here. Yes, here, where they have implemented their different prototypes and so on. So there's a lot of cool stuff that the authors have done. I think it's a really great implementation. It's very simple. Like, we were able to do it on stream quite easily. And the numbers are in front of us. I mean, we can clearly see who's performing better and by what margin. So that's the comparison. And we can see that Sieve is simple to implement. So it's not just a thing to say for a paper or to just make it look cool, right? It's actually not very difficult. All you need to know is the algorithm, which is this photo over here. And you just need to know how to manipulate a doubly linked list. That's it. Oh, okay. There's one question missed. Limit or something. If an element is called X number of times, it will be moved to a ghost cache. Yeah, that's the idea. That's the idea of having these separate caches. That's what these multi-queue caches try to do. That if an element is very popular, accessed multiple times, move it to a separate cache so that it doesn't get wiped out when you have these scanning workloads happening. So yeah, that is the main idea of the ghost cache. Let me know if that answers the question, or if there was something else. Okay, how can we generate trace data sets? Okay, so the trace data sets come from two places. One is you can either get them from production. That means you actually have, say, a cluster of servers running for, say, your website or for your company, and you collect the different cache accesses that happen. Those are called production traces, and those are basically real traces because you're getting them from a real system. So that is one case. And that actually does exist for the case of Sieve also. So I can actually show you that here. So these are all the traces of real systems. So companies like Tencent, Wiki, I think this is Wikipedia, Twitter, Meta, which is Facebook, they all publish these traces so that people can research on them. And the other option is you create these traces from a distribution. So essentially, as we all know from data science, right? Things follow a distribution. Like all of us know the normal distribution, which is like a bell curve. So in the case of web workloads, it's a well-known fact in web workloads such as web caches or CDNs, that web workloads are normally following a power law distribution, which I'll show you a photo of so that you know how it looks. It looks like this. This is how web workloads look. And the idea here essentially is that there are some objects which are very popular. They're accessed a lot of times. And there are many objects which are unpopular. They're accessed very little, very rarely. And you can imagine this. I remember giving this in the last stream as well. And it's a very good example, the more you think of it, which is of, say, Twitter, right? If a celebrity makes a tweet where, they talk about something, that tweet will be very popular. It gets retweeted. It gets, many likes, shares, comments, and so on. And that's what you would imagine on this end of the spectrum, which I'm hovering on. But then there could be tweets from accounts which are not as popular, right? Which are not as mainstream. And those will not get as many requests. They'll not get as many views, right? So they'll be on this tail end of the spectrum. So again, there are many objects where requests are not going to be a lot. And there are going to be a few objects, a few very popular objects for which there'll be a lot of requests. And this is a very well-studied fact for web workloads, that this is kind of how the distribution is. So one other option is you synthetically create the data. That means you take a distribution and you take points from this distribution and you create a trace and you run it on your input cache. So those are the two ways that you do it. Either you can do it synthetically by using by using a distribution like this that mimics your use case, your use scenario, or you take it from production. You actually connect to your servers, you measure which keys are being accessed, you record all of it in a file as a trace, and then you use that. So those are the two key ways. And while waiting for question, I'm just scanning chat to make sure I answered everything. And again, if your question has not been answered, just paste it again in chat. If I've missed it, I apologize. Just paste it again, I'll answer it. We have enough time. And there's just one thing I also wanted to mention. It's just it was an interesting thing that I noticed when I was researching about the Sieve algorithm. It's just a trivia thing to know that the power law graph, right, that I showed you, where you can see very few items are popular and a lot of the items are unpopular. This is actually indirectly related to the thing known as the Pareto principle. I'm sure you would have also heard it as the 80-20 rule, where 20% of your work is responsible for 80% of your results. So that actually has a relationship to this power law graph, where actually I think it was derived from the power law graph. That's the history of it. So the power law graph came first. It was a studied thing in data science. And then from that, informally, this idea of 80-20 or the Pareto principle came out. So that's actually an interesting trivia thing to know, that the power law graph is actually quite common for many of us to know. So yeah, I mean, there'll definitely be more advanced LRU implementations, but the thing is, those LRU implementations are not very popular because the authors do say it, I think, somewhere in the beginning of the paper. And I even remember having it in the whiteboard too. Maybe I can see if it's in the whiteboard first, where actually the authors note that in many popular caching implementations, here it is. Whether you talk about Redis, Varnish is a very popular HTTP cache. Nginx, we all know that. In all these different products, right, FIFO and LRU are still very common. And I'm talking about single queue FIFO, not multi-queue FIFO. And same for LRU, single queue LRU. The other implementations are not very common, mainly because they're not very simple. And the authors again note about this in the paper, that people or engineers choose to have simpler algorithms in production compared to more complex ones. And because of that, you will only find that many systems, like I showed, right, Redis, Varnish, Nginx, and so on, they only use simple FIFO and LRU implementations. They don't use the more complicated ones. Even though there is minimal gains with those, I mean, there are reasonable gains with those. I would not say minimal, that would not be right. There are reasonable gains with the more complex implementations, but because they are harder to implement, they are harder to maintain, they are not very popular in production. Simplicity whether it's surprising or not, is actually a very important thing for people who use these algorithms in production for serving millions of customers on the internet or anywhere else. So that is why FIFO and LRU still dominate. And this is something noted in the paper as well. And on the topic of items which can be, on items which can be possible alternatives to sieve, there are actually three main buckets, which I even remember touching upon last time, and it's like super fun to see. It's even covered in the paper briefly, that you have LRU style algorithms, LRU, FIFO. You have multi-LRU queues, which we spoke about for scanning workload resistance. And then there are actually machine learning based algorithms as well. There's one of them called CacheUs. I'll just type it in chat. CAC. Yeah, so this is actually an ML based caching algorithm. And it's quite fun to see that people are even applying ML to this. And you can imagine that maybe in some workloads, CacheUs might be better. But again, given that it's ML, it'll be very heavy on your hardware. ML inferencing is not very fast, so the latency might be very high. Even though the cache miss will be low, maybe CacheUs is very, very good at getting the right item to evict. It might still take a long time to tell you which item to evict, because again, ML inferencing, machine learning inferencing is a time consuming task. Like we all have interacted with ChatGPT or other generative AI solutions, and we can see that there is that delay. So in other ML implementations also, whether it's neural networks or anything else, there is that bit of delay, and that can be expensive in caching, which needs to be very fast and low latency. Okay, so I'll take the second question first, because that's a quicker one to answer. So it's not yet uploaded, the code. I need to upload it after this stream. Even the video, the recording of today's session will be put up. So I'll be putting both of those up, and I'll even be putting it on the channel so that it's visible and accessible for everyone. And you'll be able to play around with the code. You can make changes. You can try different trace inputs, right? Because the testing setup is already there for you. You already have the entire... here it is. You already have the entire setup ready for you to go. You can implement sieve. You can make changes. You can add a new algorithm if you want, and you can all compare them on your trace and see the results. So everything will be put up after the stream, and I'll be sharing the links on the channel as well. And coming to the first question, which was about measurements, I totally agree that it would be really cool to have implementations of all the different algorithms, whether complex or simple. Whether ML or LRU or multi-LRU, and to actually see how they perform. I would still probably say that the sieve paper does give us a good taste of the different implementations and a comparison between them. Not all, I do accept not all, but a good number of them are covered in the sieve paper. So that should give you a good taste of what sieve can do and how it compares. Let's see if I can pull a few graphs out. So these are some graphs that you can see. So you can see CacheUs. I just said the ML based algorithm. So that's here too. So you can see different workloads, and you can see the performance on different workloads over here. And they've compared quite a few. These are again not all the existing algorithms, but they have compared quite a lot, and they have made sure that they have a good variety. You can see ML based algorithms like CacheUs. They have the multi-queue ones like ARC, which I shared. You have LRU as you would expect, and you have sieve and so on. Oh yeah, definitely. The paper is a great resource. I would actually go on a limb and say that even if you're not interested in sieve per se, but you're just interested in the domain of caching, right? Like what are the caching algorithms available? What does the domain look like today? Is it just LRU and FIFO, or is it something more? Even if you just want a survey of the domain, I would still recommend looking at the paper. It's got a lot of interesting resources, a lot of different comparisons, and it name drops and compares a lot of different caching algorithms across the spectrum. So even if you're just interested in learning about the space, like what exists out there, this is a very good paper to start with. Very accessible and very useful. And probably if you are looking at a companion when you're reading the paper, again, a shameless plug, I should probably say that. I was resisting myself to say that, but I should. You can always take a look at the whiteboard. We covered a lot of things in the previous stream as well about the Sieve paper. A lot of the common simple concepts to get you going, whether it's how you should think of a cache. We even spoke about the two workloads, which I kept repeating, right? CDNs and key value caches. Those were actually demonstrated as well with visuals. So that also is here. If you're interested in the general ideas of why Sieve is better, the simplicity point which I was talking about, or the cache miss ratio and so on, that's also here. And finally, there is also a exercise here, and it's recorded as well on the previous stream, which you can take a look at. In that stream, I actually did a hands-on where I did each and every algorithm's implementation, and I showed exactly how the algorithm would work and what the miss ratio is, the miss count is, sorry. So you can see Sieve, LRU and FIFO were compared, and this was the input trace, and the miss count was counted in each. And you can again see here that Sieve was much better. So there's a whole recording of that where I did it by hand, and you can follow along with that and see step by step how these algorithms work and how you get the respective miscounts. So it's all here in the whiteboard as well. It's a good companion if you're reading the paper, and as usual, if you have questions, feel free to reach out either via direct message or via chat on the channel. I'll always be there to answer questions, any comments you have on making things better. And I think while we're waiting for any last few comments, I just want to make one appeal to everyone here that as we do these sessions, right, it's always important to keep adding feedback as we go along, because at the end of the day, for everyone here, right, and even for people watching on stream, the offer always for everyone is the same, that you provide your feedback, your comments, your suggestions on what things can be made better, whether on stream or via direct message or via on the channel as well. It's always open for feedback, suggestion, comments, anything you feel that can help make the sessions better. And in return, everyone and you yourself can actually get a much better session, right? Because again, you come here to spend your 1 hour or more of time. So, making that time worth it for yourself by giving that feedback is a great trade offer in my opinion. So just that appeal to all of you again, that anytime you feel something can be made better, any input, suggestions, comments that you may have, it's always open. And in return, you always get a better reading session going forward. So that's kind of my main sort of closing lines on always making these sessions better than the last. So just something to keep in mind. And I'll just wait a few more minutes for any closing comments. If you have any, feel free to put them in. And for people who it's getting late, no worries. Everything is being recorded. So if you need to drop for any reason, you can go ahead, because I know we have well over time. But thank you so much for joining. And yep, I'm just scanning the chat to see if there's anything else. Any final questions, any comments, feel free to put them in. And yep, I think there's no other comments or questions for today. So with that, thank you everyone for joining. I think it was a really good stream. We got what we wanted done, and we proved the point that Sieve is simpler and better than LRU for web workloads. And with that, we'll connect again soon for another session on a new paper. And hopefully on that paper as well, we do a proper code implementation and everything around it, so that we get a full idea of the paper and a hands-on as well. With that, I'll just leave you all with the GitHub repo as well, where you can keep a track. So this GitHub repo is where I'll be putting all the code implementation and the whiteboards. And yep, with that, thank you all so much for joining. See you all in a future session soon. Thanks. Have a great evening. Bye-bye.